All right. So we are going uh, to do this circuit. We'll be solving this circuit. We will do the RLC response. We'll do the transient response to the system. We are going to look for the conductor current, IL, and plot its waveform. This question is from your book, Engineering Circuit Analysis, ninth edition, that you guys are currently studying. It's an example 9.6, and it is in the on the page 348. This is a question, and we are essentially at the end, we are looking at this response for the system. This is the output response. This is the conductor current for the 2 seconds as shown here. So we'll make sure that we end up with the same results. If we end up with the same result, we have done everything correctly. What we are going to do, we haven't uh, we haven't done this unit step function, this unit step functions in the LT Spice. So it's nothing. Actually, we have done it in a different way. This is just a different way of kind of translating things into a different software. So we have a step function here, and we will see how to implement it through the source. And we have a switch uh, where it's connected across the 48 ohm resistor. So what we'll do, we're looking at this response system. If you guys have already uh, connected, I mean, you don't have to. I have already connected with the Virtuoso Cadence. I'll go to the test class, and within the test class, I'll open a new cell view. Yes, I am. And so what I'll do, I'll name it as it's an example 9.6. So I'll say lab 2 example 96. So I'm just naming it this way. Okay, we have the schematic view. So what do we have here? We have two resistors. So I'll hit the I key to instantiate. So I'll go a little bit advanced. I mean, so normally what we were using, what we were doing the browse here and going to the library manager. Instead of that, I know my components are situated within the analog library. So within the library, I'll start typing analog, and actually analog library appears here. Perfect. The cell that I would like to bring on the component that I would like to instantiate is a resistor. So I'll go with the resistor. I'll hit the enter key, and I'll hit the enter again. And I have the resistor here. So I have one resistor at the output, another resistor over here. What else do I have? We have two resistor, one inductor, one capacitor. So I'll instantiate. And now when you instantiate, actually your cell is already highlighted here. So you don't have to bring your mouse in, just write in cap. For the capacitor, enter, enter. You click the enter twice and you have the capacitor ready for you. So the capacitor goes in here. And now we need one more inductor. So just hit the I key, you instantiate, and you see your cap is highlighted. Just IND for inductor, enter, enter. And where's the inductor? It's in series with this. So I'll just bring in my inductor here. Okay, so this thing, that thing, and now we need a switch. So I'll bring the switch. So again, I'll hit the instantiate key and I'll bring SWI. So the switch is already appeared here. So I'll enter and enter. So the switch is here, which is connected across this. So I'll just keep it here. So we know when we have a switch, then we need a voltage source. Uh, Actually, not a voltage, so we need a piecewise linear source to actually activate this switch in a timely fashion. So looking at the circuit diagram, we know that the circuit was open all the time. Like I would say until time 1 second, it was so it was off, it was open. until time 1 second. But right at the next moment, which is 1.00001 second, the circuit is closed. All right. So for this, we need a piecewise linear function. In LT Spice, we were selecting a DC voltage source and we would configure it, but here we have to do it differently. We have to instantiate actually a voltage which is piecewise linear. So VPWL is the source we are looking at, and then you hit enter and then enter again. This is your piecewise linear source. All right, here it is. Then we'll bring in the ground. So I'll again instantiate G and D for the ground, enter and enter. Okay, I'll bring the ground here. I will need ground actually over here too. And finally, we have a step function here, a step current source actually. So which is 3u of minus t ampere. So again, I'll be looking at a current source, which is piecewise linear, so as to implement the step function. And what does that step function exactly means and how do we implement it? I'll just explain. So I'll go instantiate. So it is IPWL, which is current, piecewise linear current function. Enter and enter. I'll bring it right, rotate. So I've just rotated it here. Okay. Now, defining this piecewise linear function of the current. Usually, if we know that 3u minus t means that the step function has a multiplier or magnification of 3, it's an amplitude of 3, and it was 3 amp before the time t, and at the time t, it became 0 because of this minus t. So we will have to set up this piecewise linear function in such a way that the value is 3 amp at the time 1 and at time 1.001 it becomes 0. That's how we will read this 3u minus t of 3u of minus t amperes. All right. So I'll start configuring the sources. So for this one, I'll hit the Q key. Okay. So number of pairs of points. So this tells us that how many steps do we want? How many. So how our current is changing. For example, my current is having some value at time 1 and another value at time 2 and a third value at time 3 and time 4. So actually I can add those number of points here. So right now we are only interested in 2 time points. So we are okay with it. So, like I explained in LT Spice, I would not like to start this simulation at time 0. Instead, I'm using my time 1 second as a 0 second. So we're considering all the all the things happen before time 1 second, and time 1 second is our new time t, which we are considering as a 0 second. So I'm saying time 1 second, the value is 3 amps, and at the time 1.00001 second, the value becomes 0 amps. That's how it is defined. Once it is done, I'll just hit OK, and my current source is now set up. Similarly, for the capacitor, I'll hit the Q key. Capacitor is 1 divided by 240. And now there's another difference in LT Spice. When we were evaluating a fraction, we were putting the fraction value, the value to be evaluated within the curly brackets. In Cadence, you don't have to do that. We just write 1 over 240 and we are done with it. For the resistor, what is the value of the resistor? We have 48 ohm and 100 ohm. So this resistor, Q, this one is 48. This resistor hit the Q key and 100 ohms. That's done. What is the value of inductor? Inductor is 10 Henry, so I'll hit this one, Q, and 10 Henry. Okay, that's done. Let's configure this source, Q. What does that source is saying? So it is saying that the value of the voltage source was It's always difficult for me to even interpret. So it was the value of time. Before time 1 second, it was 0 volt. Okay. So at time 1 second, it was 0 volt, and actually at time 1.000. So one more thing. Let me get this second time, the time two, from my unit step, not the unit, the step function. So that we can synchronize the thing. So let me just say, okay, 1.001 is 10 volts, for example. Right now, let me just get my second time value from here. So it's 1.00. I'll just Control C, copy this one, and then I'll bring the same value here. So instead of this, okay, so that we know that the moment this step function is going to zero is the moment when the voltage, when the switch is opening. Sorry, switch is closing in this case, right? Switch is closing. Okay, so that's how I've configured. Time 1 second, 0 volt. Next time the switch is closed and it is activated. All right, the source is configured. Now the switch, we'll also have to configure the switch. So you just click it, hit the Q key, and if you guys remember, when we were configuring the switch in LT Spice, we were setting the on resistance. So when the switch is turned on or when the switch is closed, what should be the resistance of the switch? And it also, by default, it had the 1 ohm value. Similarly, the closed switch resistance is 1 ohm. That is too much. So I would just turn it into 1 nano ohm. All right. So it's just like kind of an open circuit, which is normally, expected from a switch. So a switch should not be, dissipating the current. So 1 ohm is the value. All right. Now let's connect W wire. I'll connect this, which is now connected to this. Why not? Here's the switch. I'll go Q. So Q have open resistance. So when the switch is open, what resistance do you want? It's 1 tera ohms. Perfect, because that's what we want. I mean, when the switch is open, we don't want any current to pass through. But when switch is closed switch resistance, we would like this to be of a minimum resistance because we a higher value here, and the because if the value is high, we know P is equal to VI, and V is equal to IR. So P is equal to I square of R. So R value going more means more power dissipation at the switch. That's not what we want. So I just chose a 1 nano ohms value. So it switches, I mean, just acts like like a closed circuit or a short circuit. That's what expected. All right. You're welcome. Okay, this is done. Let me just delete this thing. Okay, so I'll connect the wire from here to this, and then hmm, hmm, something is wrong here. Let me just fix it. Okay. So I'm just wiring the circuit. Okay, so 1, 2, and the resistor is connected with the switch, and we have resistor and inductor here. Okay, I'll just bring it a little bit up. Okay, so this is now defined. Let me check and save. Okay, there's no error, so we are good to go. I'll just label. So I'll start with the label. Voltage underscore C, for example. Sorry, that's not underscore C. So I'll label as V underscore C, voltage of capacitor. This is the voltage of capacitor. And then I'll label voltage underscore switch, which is here. And label V underscore L, and then label V underscore R. V underscore R, no, it won't work because it's the same node here, so it won't work. Okay, and let me, VC is there, VL is there. Okay, we are okay, we're done with it. So let me again check and save. Okay, once it's saved, let me make it big, fit the window. Okay, so now I would go to the launch and I'll say launch my ADXL. I'll create a new ADXL view, new simulation view. Does it add to example 196? Yes, that's what I want. Okay, it opens up the new tab, which ADXL. So now in ADXL, I would set up a test. Clicking here would, we'll say, use the cell name led to example 96. Yes, this is to be edited. Once here, I'll go setup environment. Within environment, choose run with 64-bit binary. Okay. We'll set simulation. I would like to choose a transient simulation, and I would just choose it for, I don't know, 5 seconds. And I'll choose the conservative for the more accuracy. Transient, stop time is 5 seconds, conservative, and I'll say okay. It's done. Now I'll have to set up the outputs. Okay, run the transient simulation on which output. So what is it that you would like to see? So I'll say set up outputs from design. So here's my design. I'll just bring it here. So I would like to see capacitor voltage. I would like to see inductor voltage, and I would like to see the current. So if I hit this node, then it will tell us the node, the current entering into the inductor. Okay, so if I hit the branch, or a node, it selects the node, the voltage. If I select the N terminal, then it selects the current through that component. I'll also select the current through this component. I'll also select the current through this component and this one. Okay, now the current and voltages, all of those things are selected. Again, for Cadence, always remember whichever node we select for the current direction is always towards the component. So if I chose this node, then the current direction is this way, okay, here towards the ground. If I've chosen this top node, it is into the to the component. If I choose the other node, which I can, then the current is towards the component, so it would be upward. All right. So I have chosen the current, I will hit the escape key and I'll go to the output setting, and you see, I mean, these are the components that we have selected to see. So what we have selected voltage of capacitor, inductor voltage, this L0 the current, the plus positive current at L0, the positive, the plus current at capacitor 0, current the through the I2 device, and the current through the R0. I'll hit the OK key. Once OK key is done, our system is ready to simulate. So I'll hit the ADXL button and I'll run the simulation. Let's wait for the simulation to complete. Okay, simulation is done and we have received uh, indication that the plots are ready. So I'll hit plot all button instead before. For example, let's just look at the current through the inductor because that's what we are looking at, right? So I'll hit the right click key over this area where the plot is, right click and the plot. And this is going to give me the plot of inductor. So that's the inductor plot. I'll just bring it to, okay, a little bit. Okay, so now that's what my current through inductor is. And you see it starts at nearly 2 amps, goes up to 2.68 or something. Where is my output? So here. So nearly starting at this point, going around 2.6 amps, and then at the base it goes around minus 1.3 something something, and it goes to here minus 1.3 something something here, and then this is the plot. I mean, it goes this way until it settles down and reaches the steady state. So uh, this is a confirmation, first of all, that we have done the simulation correctly. All right, but now there are more quantities of interest. So let me just plot all of them. Okay, so we will learn a little bit manipulation also here. So when we slide this window, we can actually move the area to our interest. So I'll just slide by this time. Now look at the left. We have talked about this just as a reminder. So we know the voltage of capacitor, voltage of inductor, the current through inductor, current through capacitor, to the current source, and our, oh, we should have selected the voltage switch voltage. That was also important. We forgot to select that. Well, I'll select it. I'll show you how to do it from now. I mean, for example, this is already done. So what I'll have to do, I'll have to again go from here, go to ADXL. Let me just close this quickly. Close this ADXL test, and I'll hit the window, and I'll say from design, and I'll just select the voltage switch. I'll escape. I'll go here and see voltage switch was selected. Say OK, and run the simulation again. It's all captured, so you don't have to worry. If I go quickly, you will be able to see it in the video later. So the plots are now ready. So let me now plot all. Okay. So we have voltage of capacitor, voltage of inductor, voltage of switch. I'll keep L current through inductor, current through capacitor, current through the current source, and the current through the inductor source. Now, if you see here, in order to zoom, you have to right click. Okay. So this is the switch. So switch was 0 until 1, and then it turned to 10 volts, which means it turns on at the 1 second, and this is actually fulfilling the requirements. So the switch was 0, and at times 0, it before time 0, it was open, and at time 0.0001 some seconds it was closed. So we have seen that it's happening. Now that's not of my interest, so I will see the voltage of capacitor. So that's the voltage of capacitor. In order to fit the plot, you can click anywhere and just hit the F key, and actually it will fit. So this is the voltage of the capacitor, how the voltage of capacitor is behaving, and this is the voltage of inductor. So nearly on top of it. All right. So that's the voltage capacitor and that's the voltage inductor. They are in phase, following each other. And let me get the, yeah, here's the current through the inductor. and I would like to see the current through the source here. So current through the source, we saw that it has a, let me just, so current through source, it just says that, I mean, before 1 second, it had a value, and then it turned into something like 10, sorry, the when we are looking at this plot, we have to, I mean, if we see that this area has been grayed, then you know that you have to look at the current. So here's the highlighted area. So that's how you would know that which area you will be looking. All right. So the current source we set was, it was 3 amperes before the time, and then at time 0 it turned out to be, so at time, sorry, at time 1 second it turned to 0, so which is here. All right. And so that's all about how the plots should work. Let me just quickly see the final. Let me fit. Yeah, that's how the plots would be. And after this, I'll explain the requirement for the lab once again. This is done. Let me just stop the video. I want to keep it short.